Good morning, sir. My name is Ensa Ignesh of class ITB. My roll number is 21951A12776. Today I'm going to present a concept video on LSE subject. So my topic is about finding the inverse of a matrix using Cayley-Hamilton theorem. So let's have a look on the contents. About Arthur Cayley, about William Rowan Hamilton, about Hamilton theorem. Examples: Cayley-Hamilton theorem is used to find means the inverse power of the matrix, and the finally applications. Arthur Cayley. Arthur Cayley, August 16, 1821 to January 26, 1895, was a famous British mathematician who specialized in algebra. He was instrumental in the establishment of the modern British pure mathematics school. Cayley used to have a lot of fun solving complicated arithmetic problems as a kid. He was accepted into Trinity College, Cambridge, and excelled in Greek, French, German, and Italian as well as mathematics. For 14 years, he worked as a lawyer. And William Rowan Hamilton. Sir William Rowan Hamilton, from 4 August 1805 to 2nd September 1865. He was an Irish mathematician and Royal Astronomer of Ireland at Dunsink Observatory. He was an Andrews Professor of Astronomy at Trinity College, Dublin, and Andrews Professor of Astronomy at Trinity College, Dublin. He was Andrews Professor of Astronomy at Trinity College, Dublin, and Andrews Professor of Astronomy at Trinity College, Dublin. Optics, classical mechanics, and abstract algebra all benefited from his efforts. His work in theoretical physics was significant, particularly his reformulation of Newtonian mechanics, now known as Hamiltonian mechanics. It currently plays a crucial role in both electromagnetism and quantum mechanics. He is primarily recognized for inventing quaternions in pure mathematics. Now let's see what is Cayley-Hamilton theorem. In linear algebra, the Cayley-Hamilton theorem, named after the mathematicians Arthur Cayley and William Rowan Hamilton, states that every square matrix over a commutative ring, such as the real or complex field, satisfies its own characteristic equation. If A is a given matrix n by n matrix, and it is the n by n identity matrix, then the characteristic polynomial of A is defined as P of lambda is equal to det of lambda in minus A, where det is the determinant operation and lambda is a scalar element of the base ring. Since the entries of the matrix are linear or constant polynomials in lambda, the determinant is also an nth order monic polynomial in lambda. The Cayley-Hamilton theorem states that substituting the matrix A for lambda in this polynomial results in the zero matrix, that is, P of A is equal to 0. And so the powers of the A obtained by the substitution from powers of lambda are defined by repeated matrix multiplication. The constant term of P of lambda gives a multiple of the power A, which power is defined as the identity matrix. The theorem allows An to be expressed as a linear combination of the lower matrix powers of A. When the ring is a field, the Cayley-Hamilton theorem is equivalent to the statement that the minimal polynomial of a square matrix divides its characteristic polynomial. The theorem was first proved in 1853 in terms of inverses of linear functions of quaternions, a non-commutative ring, by Hamilton. This corresponds to the special case of certain real 4 by 4 real or 2 by 2 complex matrices. The theorem holds for general general quaternionic matrices. Cayley in 1858 stated it for 3 by 3 and smaller matrices, but only published a proof for the 2 by 2 case. The general case was first proved by the Fabinius in 1878. So here's the example for the Cayley-Hamilton theorem. Before going to this, let's recall the statement of the Cayley-Hamilton theorem, that it states that every square matrix has its own characteristic equation. It satisfies its characteristic equation. So here's an example. Uh, Verified Cayley-Hamilton theorem for A matrix is equal to 1, 4, 2, 3. Find A inverse for that. So we know that A minus basic characteristic equation is A minus lambda is equal to 0. So he substituted the matrix A and minus lambda into here I means identity matrix, that is 1 0 and 0 1 for 2 into 2 matrix is equal to 0. After solving, we get the matrix, we get the equation as lambda square minus 4 lambda minus 5 is equal to 0. So the characteristic equation of A is P of lambda is equal to lambda square minus 4 lambda minus 5 is equal to 0. So for the Cayley-Hamilton theorem verification, we need to replace lambda with A, that is P of A is equal to A square minus 4A minus 5I is equal to 0. This is the first equation. We need to see that at constant place we need to add identity matrix. That implies A square is equal to 1 4 2 3 and 1 4 2 3. So if we multiply, we get the matrix as 9 16 18 and 17. So after solving the equation, we get 2 by 2 as a null matrix. 2 by 2 null matrix. Hence it proves that every square matrix satisfies its own characteristic equation. Here's another example for the 3 by 3 matrix. Verify the Cayley-Hamilton theorem for the matrix C is equal to 2 minus 1 2 minus 1 2 minus 1 1 minus 1 2. So the characteristic equation polynomial is given as, so after we need to substitute the characteristic equation, that is as previous one, that is A minus lambda I is equal to 0. So after solving that equation, we get this equation, that is c cube minus t square c square plus t1 c minus t naught. So here he used another method. So now after solving, we get the equation as, now p of c is equal to c cube minus c square plus 8c minus 3i. Now next, so we get the, so after solving each one, like c cube is equal to, we get 29 minus 28 38 minus 28 22 23 minus 28 22 minus 22 29. For 60c square, we get this matrix, that is 42 minus 36 54 minus 30 36 minus 36 30 minus 30 and 42. For 8c, we get 16 minus 8 16 minus 8 16 minus 8 8 minus 8 16. For 3i, we know that it we got 300 030 003. Now after substituting these values in the previous equation, that is c cube minus 6c square plus 8c minus 3i, so we get a null matrix. That proves that Cayley-Hamilton is verified. So let's see what the theorem is used to find. Cayley-Hamilton theorem is used to find inverse and power of a matrix, and only inverse of a matrix and only power of a matrix. So let's see how to find a inverse of a matrix using Cayley-Hamilton theorem. So here's a question: find inverse of a matrix using Cayley-Hamilton theorem. So given matrix is A is equal to 3 1 1 minus 1 2 1 1 1 1. So to apply the Cayley-Hamilton theorem, we must first uh, determine the characteristic equation of the matrix A. So here it is given as A minus Ti. So we should consider T as lambda. It's a general equation. So after that we get 3 minus T 1 1 1 minus 1 2 minus T 1 1 1 1 minus T. So after that we get, so after solving this determinant, we get equation as minus T cube plus 6T square minus 10T plus 2 equation. And after that the Cayley this theorem yields that so we need to convert the equation into Cayley-Hamilton theorem general equation, that is we need to substitute lambda as A or T as A. So P of A is equal to minus A cube plus 6A square minus 10A plus 2I. So after solving we can get that we can get a null matrix. So after from this equation we can find the inverse of the matrix. So rearranging terms, we have 2i is equal to a cube minus 6a square plus 10i. As we get the null matrix, we can send these equation to the right side. We can equate to the identity matrix. So after this, 2i is equal to a into a square minus 6a plus 10i. We get a inverse is equal to a half into a square minus 6a plus 10i. So basically we know that a inverse is equal to a into a inverse is equal to identity matrix. So that formula is used here. So now first we have to find a in a square minus 6a plus 10i. So after multiplying a into a, we get 9 6 5 minus 4 4 2 3 4 3, and 6a we get 18 6 6 minus 6 12 6 6 6 6, and so a square minus 6a we get, after solving these all the equation, we get as for the equation a square minus 6a plus 10i, we get 1 0 minus 1 2 2 minus 4 minus 3 minus 2 7. So we need to equate to the a inverse, that in the equation a square a inverse is equal to half into a square minus 6a plus 10i. So after solving the equation, we can get a inverse is equal to half into half of 1 0 minus 1 2 2 minus 4 minus 3 minus 2 and 7. So we know that we have now discussed how we can get a inverse for the given matrix by using Cayley-Hamilton theorem. We can also find the power of the matrix by similar method. So now let's see the applications of the Cayley-Hamilton theorem. The Cayley-Hamilton theorem forms an important concept that is widely used in the proofs of many theorems in pure mathematics. Some of the important applications of this theorem are listed below. That is, the Cayley-Hamilton theorem is used to define vital concepts in the control theory, such as the controllability of linear systems. In commutative algebra, Nakayama's lemma can be proved using a generalization of the Cayley-Hamilton theorem. The theorem of Jacobson can be proved using the Cayley-Hamilton theorem. So these are the applications of the Cayley-Hamilton theorem. Thank you.